Hi, I'm Rami Tamimi. Behind me here is a surveying total station, and this is the iPhone 13 Pro. Today we're going to be analyzing the iPhone 13 Pro's LiDAR sensor, and we will be comparing the data from this LiDAR sensor to a high-accuracy surveying total station. Now what we have here is Apple's new iPhone 13 Pro. They've included their second-generation LiDAR sensor next to their 3 camera sensors that they've all upgraded. So the question is, how accurate is this LiDAR sensor in comparison to a total station? A robotic total station is one of the most accurate pieces of equipment used in the surveying industry. The relative accuracy that we can achieve with a surveying total station is usually between 100th and 200ths of a foot. So it's safe to assume that this piece of equipment is a great benchmark to use for testing relative accuracy. A total station like this can cost anywhere between $20,000 to $60,000 US, and a professional grade LiDAR sensor can easily run you up to $180,000. By taking several measurements of features using a total station and then extracting those locations from the data set we get from the LiDAR sensor, we can calculate the relative accuracy of the iPhone 13 Pro's LiDAR sensor. Now, if you enjoy this type of content and you want to learn more about surveying and LiDAR sensors, be sure to subscribe to the YouTube channel and turn on the bell notification so you're notified anytime we release new videos. Now, for today's video, we're going to be measuring 15 different points, and I've marked all these points using a piece of chalk, and I'm going to go over exactly why we're analyzing these points and what we hope to achieve by measuring these specific locations. Points number 101 and 102 will be used to analyze how the iPhone's LiDAR sensor can handle the elevation change between a curb and a gutter. Points 103, 104, 106, 107, 109, 110, and 111 will be used to compare a feature extraction of the sidewalk. We want to see how well the iPhone's LiDAR can position this sidewalk in comparison to the total station. Point number 105 is a PK nail. A PK nail is generally used in the surveying industry to set control points. So I'm curious to see if the LiDAR sensor is going to be able to pick up this feature and whether or not the accuracy of this point using the LiDAR sensor is going to be relatively the same as the total station. Point number 108 is the center of the storm sewer manhole. Manholes are really common utility structures that we see in the construction industry. So by scanning it with the LiDAR sensor, I want to see how accurately we can get to the center of this manhole, as well as identifying the rim elevation. Points number 112, 113, 114, and 115 will be used to map out the curb and gutter, as well as analyze the change in elevation, just like we did with points 101 and 102. And that's it. That is what we're going to be surveying today. This is a very realistic example of what we would do in the industry. So by comparing the total station and the LiDAR sensor on a site like this, we should be getting a real-world example of what to expect in terms of relative accuracy. All right, let's start by setting up the survey total station. If you're unsure on how to set up a surveying total station, check out this video that I made a while back. It kind of goes over the fundamentals of setting up the tripod, placing your total station over a point, and leveling it as precise as possible. So watch that if you don't know how to set up a total station, and then come back to this video. Alright, and I am measuring an instrument height of 5.04 feet. Okay, and I'm going to set my back sight right here, make sure the bubble is in the center, and point it in the direction of the total station. Now I'm going to take a distance using the total station to the back sight, and using this distance, I'm going to then create my local coordinate system. Okay, and we're pointing the total station to the back sight. I'm going to go ahead and take a reading. Okay, and after taking that reading, we can see that the distance between both the total station and the back sight is 24.009 feet, and the elevation of the back sight is 100.289 feet. So using these two distances, we can now assign coordinates for our back sight and set up our control network. And now we're at the setup menu. We are occupying point number 1, which is where the total station is, instrument height, which is the total station's height, which we measured at 5.04 feet, back sight point, which is point number 2, and the height of the back sight is 5.29 feet. I'll hit back sight and check. As you can see, we have 0 error, which means that our control network is set up. I'll hit set angle, And now we're ready to go. Now I'm going to be using this little 1.45 foot rod. This little rod will help us stay as close as we can to the ground and minimize any kind of errors. Usually a 6-foot rod is fine. It really won't create that much error, but for the purpose of this experiment, I want to try to do this as clean as possible. So that is why we're going to use this 1.45 foot rod for all of our foresights. I'm also going to attach this receiver sensor on top of the prism so that we can utilize the robotic functionalities in this total station, and it'll find the position of this rod without me having to point at it. This does not impact the height of the rod as this is going on top of the prism. All right, looking good. I'm gonna start by setting the rod here on point number 101. Okay, and the bubble is leveled. All right, now I'm gonna have the total station search and find the prism. All right, perfect, we're locked on. Okay, now that we're locked in on the prism, I'm gonna go ahead and assign this as point number 101. This is a gutter, so I will call it gutter. And the prism height is 1.45 feet. And now we can take this observation. All right, now I've set this up on the curb, so I could just change this to curb, and we'll take the next shot. And that's pretty much the procedure. I'm gonna go ahead and do this for the rest of the 15 points. Okay, point number 103, point 104, point 105, point 106, 107, 108, 109, 110, 111, 112, 113, 114, and finally 115. And there we go, 15 points. And as you can see, all of our points are here. All of them are also labeled appropriately based on the feature that we measured. I'm just gonna go ahead and finalize this by checking into our backside and making sure that our horizontal angle is still set to 0. Okay, and measure. And we can take a look here and see that our horizontal angle is 0 degrees. So we're all set with the total station measurements. Now that we're done taking measurements with the total station, it's time to test the iPhone 13 Pro's LiDAR sensor. Before we get started, I just want to let you guys know that I started surveyshirts.com. Here you'll find a large range of surveying apparel. The shirts come in different sizes and colors, so please check out surveyshirts.com. Let's get more survey shirts out there for all of our fellow surveyors to wear. Now I'm going to be using the 3D scanner app. This app is available for free on the App Store. So I'm going to go ahead and open up the app. And as you can see here, we are in the low res mode. I'm going to switch over to high res. And with the high res on, I have some options that I can go through. First, I can select the confidence level that I want my scan to have. The higher the confidence, the more accurate the position of the point is in relation to other points. This also means that there was a strong return on the points. So by setting this confidence level to high, you're going to have a lower number of points because the threshold for high accuracy points is a lot higher. So I'm going to set this to high actually because I want to have the most accurate points when doing the scan. Next we have the range. The range will tell us how far out you want the scan to go. If I have a short range, it's only going to capture points that are a lot closer to me. The more I increase the range, the further points are then collected. Of course, anything after 5 meters will not be collected. I am going to set the range to 5 meters because I want to collect as many points in our field of view. Next we have masking, which if we're doing modeling work, I'll definitely want to mask the object that I am scanning. I don't want the background to show up if I'm doing modeling work, but because we're doing mapping work where we're measuring the terrain, I want to make sure we capture everything. So I'm going to leave masking off. And finally, we have resolution. The resolution indicates how much detail we want in our scan. If we increase over to 20 millimeters, this will reduce the resolution because now we're scanning at a much higher scale, which is why you see the house there. But if I lower the resolution, I can set it to 5 millimeters, which would scan something as detailed as an apple. Now that I have all my settings in place, I can go ahead and start scanning our site. Okay. Okay. Looking good. All right, and as you can see, we have our scan right here. Looks to be pretty good. I'm gonna go ahead and process the colorized scan now. All right, and there we go. The colorized scan is done. You can go ahead and turn on the tin. Look at that. Look how incredible that is. I love looking at this interface and being able to see all the connection points for all the points that were scanned using the LiDAR sensor. Now, let's take the data from the total station as well as the scan that we got from the iPhone 13 Pro's LiDAR sensor and analyze it in the office. Why, hello there. Welcome to my office, which is actually in my house. All right, let's import all the data into AutoCAD Civil 3D. We'll start with the total station points. I'm gonna go over to Insert, Points from File, and I'm going to Add Points, and I'm going to select my iPhone 13 file, and there we go. The point format is point number, northing, easting, elevation, and description. So all of my points are here. We'll go ahead and just click OK. And there we go. We have all of our points. Here's point number 1 where the total station was. Point number 2 where the backsite was. And then everything curb gutter, curb gutter, curb gutter, the sidewalks, PK nail, and the manhole. Okay, now let's go ahead and import our point cloud that came from our iPhone 13. I'll come up to the Insert tab. Under Point Cloud, I'll select Attach. This is my point cloud file, so I'm going to open it. Now it's going to ask me where I want to place this point cloud. It doesn't really matter where I place it because I'm going to end up aligning it to the points that I shot with the total station. Relative path is fine. Select insertion point. I'm going to just do 4950 because 5000, 5000 is where the site is located, so I'm going to move it 50 feet off of that site. 4950. Elevation, I'll just set this to 100 because that was the elevation of our assumed coordinate system. The scale, we'll keep it set to 1 because we don't want to rescale the point cloud, and the rotation, we'll keep it at 0. And we'll hit OK. And there we go. Point cloud is here. If I select it, you can see the insertion point 4950, 4950, elevation 100, 0 rotation, and scale of 1. So now when you look at this point cloud, you can see we have the RGB values of all the points. The points are kind of small, so I'm going to select this and increase the size to, I don't know, 7. That way when I zoom in, I can really see the points. So I can see it right there. Now, it's not the best practice to use the RGB values because there could be a shift between the LiDAR points and the camera that was used to take the colored picture, because the LiDAR points are then assigned colors based on those pictures. So if there's any kind of drift between the two sensors, then the colored points are going to be drifted. The best way to visualize this is going to be by setting this over to normal, and you can actually see where there are changes in elevations. So what I'm going to do, because it's really difficult to pick the points in this visualization setting, I'm going to pick the points with the RGB values, but then I'm going to check the normal visualization to make sure that it's actually where it needs to be. So we'll switch back to scan color, and now we're going to align the point cloud to the total station points. It'll ask me to select an object. I'm going to select my point cloud, and then it's going to ask for the first point. So the first point is going to be right here, and I see some red, so I think that's where the point is. And now I'm going to select 104. Now it's going to ask for a second source point. So the second point, we said, let's do this bottom point here, and point number 112 is over here. Now it's going to ask me if I want to scale my point cloud, and I'm going to say no because I don't want to change the locations of these points. So the relative distances between all these points will stay the same. It's just now they're being aligned to the total station points so that we can have everything on the same coordinate system. So I'm going to say no. And that's it. The point cloud is now on the same coordinate system as the total station points. All right, now we're going to start the feature extraction from the point cloud that we got out of the iPhone 13 Pro. To begin, I'm going to freeze the total station points so that we're not confused by them when we go to select the points on the point cloud. I created a layer called LiDAR points, so I'm going to select that and set it as my current layer. All right, so we're going to go to points, point creation tools, and if I bring this over here, I can take a look at some of these settings. The biggest one is the default layer. We're going to use the current layer. And when I come down to point identification, we're going to start with point number 201. All points that are 100 are going to be points that came out of the total station. All points that are 200 will be points that we extracted from the point cloud that came out of the iPhone 13 Pro. So all this looks good to me. I can close out of that and start creating points. So we'll come down here. This is our first point, and I can see where there's the red marking, so I will select here. It'll ask me for a description. This This is a gutter, and now it's assigned an elevation. This is the elevation that it's taking from the point cloud, so we're always going to accept this elevation because that's our measured elevation from the data set that we have. All right, if we look over here, point number 201 is created. All right, and I've tilted the point cloud a little bit here so I can at least see the edge of the curb and select the right point. So this right here, curb, and give it the elevation. And this is the procedure of feature extraction. So I'm gonna quickly go through the rest of the 15 points and extract all of them. Okay, point number 103, concrete. Point 104, concrete. Point 105, the PK nail. Point number 106, concrete. Okay, point number 107, concrete. Point 108, manhole, storm sewer. Point number 109, concrete. Point number 110, concrete. Point 111, concrete. Point 112 is a curb. 113, gutter. Point number 114, curb. And finally, point number 115, gutter. All right, if we take a look here, all the points are in there. I'm gonna go ahead and freeze our point cloud. These are all the points that we just extracted from the point cloud. I'm gonna bring back the point cloud, and I wanna change the visualization of the points to normal so that we can take a look and see and make sure everything that we selected is exactly where it needs to be. So now we can highlight the curb, gutter much more defined, and it's not relying on the RGB values. Okay, this all looks to be in the correct place. Yep, this curb and gutter looks good. Where it's really gonna show is where there's like intersection of features, like right here where there's a driveway and a curb. So this point looks to be in the correct spot. This looks to be the center of the manhole. This right here along the sidewalk and driveway looks good. So yeah, all the points are matching up to the point cloud like it should. So that means the camera sensor and the LiDAR sensor calibrated correctly and all the RGB values are accurately placed. So now let's go ahead and export all the points so that we can bring it into Excel and compare all the numbers. All right, point number 101, which was the first gutter shot that we took, we have a difference in northing of 0.04 feet, difference in easting of 0.1 feet, and then distance in elevation 0.22 feet. I've also included the millimeter conversion. So if you're outside of the US and you want the metric differences, there you go. This honestly isn't too bad. I feel like the elevation is a little more than I thought it would be. I thought it would be a little less than that. Overall, positioning wise, we're only off by a 1/10. That's pretty good. When we look at the curb, we have slightly more error, 0.08, 0.14, 0.19 in the elevation. So yeah, again, I'm seeing a little more error than I would have liked. Point number 103, we are right on in the northing, pretty much right on in the easting, and only a 1/10 off in elevation. And I like that. That's pretty good. That tells me that within that distance between point 104 and 103, there wasn't too much of a difference in there. 104 we really can't use to test the accuracy because we used it to do the alignment. You might be wondering why this isn't 100% zero, and that's because I didn't pick the exact same location when I did the alignment versus when I did the feature extraction. So forgive me, but I was off by about 1/100 of a foot. Nonetheless, let's move on to the next point. That PK nail was off about 1/10 in the northing and easting and only 3/100 in the elevation, so that's pretty good. I'm pretty satisfied with that one. Point 106, which was along the concrete, we were off 8/100 in the northing, right on in the easting, and pretty much right on with the elevation, so that's pretty good. 107, which is a point on the concrete across from the manhole, we have about 2/10 in the northing, 1/10 in the easting, and 1/10 in the elevation. That's actually pretty good. I know the northing's a little high, but the elevation came out really good on that one, so I'm pretty satisfied. The manhole that we shot, 108, 0.17, 0.13, and then about 2/10 in the elevation. Not too bad, actually. I think that's pretty good. Definitely not something I would trust for any kind of design work because that rim elevation really needs to be much more accurate, but for what we did, it wasn't too horrible. Looks like points number 209, 210, and 211 share about 2 to 3/10 difference in the northing, 10 to 15/100 in the easting, and about 2 to 3/10 in elevation. And that's because we're moving about 30 feet away from the start of our scan. So I think that 30-foot move did cause a little bit of drift error. So I can see why that would be. Point number 112, northing and easting, 2/10 and 1/10. Again, that's probably from the the drift from how far out we went. I'm not going to compare the elevation because we use that point for alignment. Points 113, 114, and 115, which were the curbs and gutters, they seem to all share very similar results. 2/10 in the northing, about 1/10 in the easting, 5/100ths for 115, so that's pretty good. And elevation 1 to 2/10. And so overall, my thoughts, you know, if you're looking for 1 to 2/10 of accuracy, you'll probably end up finding it. There's still drift error that is occurring with the iPhone's LiDAR sensor, so this isn't perfect for mapping. However, if you supplement it with some additional control points, recognize the margin of error and what your realistic expectations should be, the LiDAR sensor is relatively accurate. It does a pretty good job of maintaining its positional accuracy, and the RGB values are lining up pretty good with the LiDAR points, so you shouldn't have any issues using the RGB point cloud to do feature extractions. I definitely want to do more testing with this iPhone and start incorporating more control so that we can increase the accuracy as much as possible. I hope you guys enjoyed today's video. If you did, please like the video. I put a lot of effort into this and I really appreciate you guys watching this all the way through. If you enjoy surveying, LiDAR, iPhones, all this great technology, be sure to subscribe to the YouTube channel and turn on the bell notification so you don't miss out on any future uploads. Check out our private Facebook group. The link is in the description. We have surveyors from all over the world talking about the exciting projects that they're working on, so definitely be a part of our community and share with us all your surveying experience. Be sure to check out surveyshirts.com if you want to buy surveying apparel. And with that, I will see you guys next time.